Bismillahirrahmanirrahim. Assalamu alaikum, students. Today, our topic is capacitors. So, right, capacitors. What is a capacitor? Definition. So, capacitor is defined as a device that stores energy that stores energy in an electrostatic field, right? So it's a device that stores energy in an electrostatic field. Where from that field comes, for that we have to first charge the capacitor. So we charge the capacitor. For charging the capacitor, we can use a battery. Then that creates electric field between the plates of the capacitor, and in that electric field resides energy which can be taken back from the capacitor by discharging the capacitor. We will show it and understand it. First, what are its uses? For example, we use flash bulbs. Now, flash bulbs require a short burst of electric energy. Flash bulbs require a short burst of electric energy. So we use capacitors to provide them these short bursts of electric energy, because battery cannot generally provide short bursts of electric energy. Short burst of electric energy means we have to provide a flash bulb large energy in less time. Now, we can draw energy from a battery also, but from a battery, we can get energy only slowly, not rapidly. But capacitors have a property, they can release energy rapidly within milliseconds. So, flash bulb is an example where capacitors have a use. I write here uses of capacitors, right? So we use capacitors to drive flash bulbs. Similarly, larger capacitors are used to provide intense laser pulses in attempts to induce thermonuclear fusion in tiny pellets of hydrogen, right? Capacitors are also used to produce electric fields. To produce electric fields. For example, we use parallel plate capacitor, we charge that, then there exists an electric field between its plates. That electric field can be used to deflect beams of charged particles. So we use capacitors to produce electric fields also. Capacitors have other important function in electronic circuits, especially for time varying voltages and currents. For example, in transmitting and receiving radio and TV signals, capacitors are fundamental components of electromagnetic oscillators. Electromagnetic oscillators is a kind of circuits. So capacitors are fundamental components of electromagnetic oscillators. So as components, I write capacitors. Capacitors are fundamental components of electromagnetic oscillators. So they are fundamental components of electromagnetic oscillators. So this is another function of capacitors. Now, how we form a capacitor? We have two conductors. Let it be one conductor, another conductor. They are isolated from one another and from their surroundings. I write two conductors isolated from one another and from their surroundings form a capacitor. Right? So any pair of conductors isolated from one another and from their surroundings form a capacitor. So if these are two conductors, they form a capacitor. And when we say they are isolated, by that we mean they are electrically isolated from one another and from their surroundings. Right? The two conductors can have any shape. Sorry, first let me fix it. So these two conductors can have any shape. So regardless of their shape, the conductors forming the capacitor are called plates of the capacitor. A capacitor has two plates, right? What we do in order to charge this capacitor, we connect it with a battery. We connect it with some battery. Battery, this is the positive terminal, this is the negative terminal. So when we connect battery across the plates of a capacitor, it supplies some potential difference V. So what happens? Electrons are transferred from one plate to another plate. So that gives plus Q charge to one plate and minus Q charge to another plate. Right? So when we apply potential difference across the plates of the capacitor, charge is created. So electrons are taken from this plate and they are driven to another plate. So this plate gets excess negative charge and this plate gets excess positive charge. Now, if we see The total charge on any charged capacitor is 0. This plus Q minus Q, when you add it, is 0. A capacitor has a property that if you take the magnitude of charge on either plate, let it be Q. So let Q be the magnitude of charge on either plate, and V is the magnitude of potential difference across the plates. So then capacitor has a property that this Q is directly proportional to V. I repeat, if Q is the magnitude of charge on either plate of the capacitor, which is Q, and V is the magnitude of potential difference between the plates, then there is a proportionality between Q and V. Now the constant of proportionality is written as C, where this constant of proportionality C, where C, the constant of proportionality, is called capacitance. It is called capacitance. Now every capacitor has a capacitance. Now capacitor is specified by its capacitance. When we put some capacitor in some circuit, its behavior in that circuit will be specified or characterized by its capacitance. Larger the capacitance of a capacitor, as you can see from this equation, for a given potential difference, that capacitor will have more charge on the plates, right? I repeat, larger the capacitance of a capacitor, larger the charge created on its plates for a given potential difference, right? And since the electric field is created due to the charge creation on the plates, and we know energy resides in the electric field, so we can say larger the capacitance of a capacitor, larger is the energy stored in the capacitor for a given potential difference, right? Now from this equation, you can see the SI unit of capacitance is farad, which is 1 coulomb per volt. Coulomb per volt is the SI unit of capacitance, which is called farad. So it's SI unit of capacitance. The capacitance of a capacitor C depends on the shapes and relative positions, the shapes and relative positions of the plates. So if you change the shape of the plates of the capacitor or their relative position, by that you can change the capacitance of the capacitor, right? It also depends on the material, also depends on the material that fills that fills the space between the plates. So it depends, capacitance depends on the geometry of the capacitor. It depends on the material that fills the space between the plates. You might know we fill the space between the plates of a capacitor by materials called dielectrics, which are basically insulators to enhance their capacitance, right? Now we will take some capacitors. We will assume the vacuum between the plates. We assume there is no material between the plates of the capacitor, there is vacuum. We calculate their capacitance. We take capacitors of different geometries and we calculate their capacitance and see how their capacitance depends on geometrical parameters. So our next topic is calculating the capacitance. As we said, the capacitance depends on the shape and relative positions of the plates. That means it depends on the geometry. So we have different kinds of capacitors. We have a capacitor called parallel plate capacitor. We have another capacitor called cylindrical capacitor. We have a spherical capacitor. And we can treat an isolated sphere as a capacitor, which actually is a limiting case of our spherical capacitor, right? Now we will take them one by one and calculate their capacitance. And what will be our plan of calculating the capacitance? First, I tell you that. So our plan of calculating the capacitance of the capacitor will be, we will first assume some charge Q on the plates. Then we will use Gauss's law. We know the Gauss's law relates the electric field with the charge. So first we will assume some charge on the plates. Then we will use Gauss's law and find the electric field between the plates in terms of the charge on the plates. Then third thing will be, we will be calculating potential difference between the plates from the electric field. You know the relation VB minus VA is equal to minus A to B E dot ds. We will make use of this equation, right? Then once we find the relation between potential difference and charge, we will make use of Q is equal to CV, this relation, which is the defining equation of the capacitance. So I repeat, first we assume some charge on the plates of the capacitor. Then we use Gauss's law to find electric field in terms of charge. Then we find potential difference between the plates in terms of charge by substituting the value of electric field obtained from Gauss's law into this equation. Then the resulting equation we compare with Q is equal to CV and calculate the capacitance. So first we take the parallel plate capacitor. So my first capacitor is parallel plate capacitor. We'll draw the figure. So this is our charged parallel plate capacitor, right? So on upper plate there exists plus Q charge, on lower plate there exists minus Q charge, right? Parallel plate capacitor is simply we have two parallel plates. This diagram shows the cross section of three-dimensional geometry. It's simple. You have two parallel plates which are placed in parallel with each other. Let D be the spacing between the plates and A be the area of cross section of the plates, and we have charged it by some battery. There is existing electric field shown by these lines, and we are assuming that it is uniform. In parallel plate capacitor, electric field is uniform in practice also, provided the plates are close enough and large enough and we are far from the ends. If we assume electric field is uniform, now what is our next step? We draw a Gaussian surface. Let me use another color. So I take a Gaussian surface. So this is my cubical Gaussian surface. You can see this Gaussian surface will have 6 faces, one, second, upper one, lower one, front one and back one. But flux will be contributed by only this face, lower face, which will have the same area. The portion of the Gaussian surface which contributes to the flux will have the same area as the area of cross section of the plates. So applying Gauss's law, let me use another color. Applying Gauss's law, closed integral E dot dA is equal to Q by epsilon naught. Here Q is Q because charge inside the Gaussian surface is positive charge Q on the plate, so Q is Q. Electric field and area vectors are parallel, so E dot dA becomes just E dA. Theta is 0, cos 0 is 1. And when you integrate over this surface, which is of the Gaussian surface, which is parallel to the plates, that will become total area A. So it will simply be, I write directly EA equal to Q by epsilon naught, right? So E is Q by epsilon naught A. So I name it first. I have calculated the electric field between the plates of the parallel plate capacitor in terms of the charge. Next is what we do when we use this equation, we have to select our path of integration. What we do, we move from positive plate to negative plate. So I show my path of integration. So this is my path of integration. So when I take this path of integration, I move from positive plate to negative plate, then this equation will be V plus minus V minus. This final point is B. I am moving to negative, sorry, it will become my final place is negative plate. Final point is here B. It will be V minus minus V plus equal to minus A to B. Now I will write in terms of I am moving from positive plate to negative plate. It will just become EDS, right? It will become V final, which is negative plate, minus V plus, which is initial plate potential of the positive plate. This is potential of the negative plate, and it is formula minus of the formula. Then you are moving from positive plate to negative plate. It will become EDS because electric field is downward, displacement is downward. So E dot ds is just EDS. That now this is what it is, the potential difference between the plates. And it will, if I take this way my path of integration, this potential difference is going to be negative quantity because here is negative. What we do, we represent by V the magnitude of potential difference, which is always positive. Magnitude of potential difference. So if V is my magnitude of potential difference between the plates, this negative will disappear when I take the magnitude only. That means I have then V equal integral plus to minus EDS, right? Plus to minus EDS because I am taking the part of integration from positive plate to negative plate, and V is the magnitude of the potential difference, right? Now, using first for E, I get plus to minus. Instead of E, I will write Q by epsilon naught A, and then I have what? ds. What I have done, I have used it first, this equation. First, I have replaced E by Q by epsilon naught A. Right. Now, since the distance I move is d, so if I take 0 at positive plate, my ds is 0, then here ds will become, displacement is here 0 here, ds will become what? If I have to put the limits on ds, here it will become d. That means this integral will become 0 to d q by epsilon naught a ds, right? Now q by epsilon naught a can be taken outside as it is constant as we move between the plates. Then inside the integral 0 to d, we will have ds, which is just d. So it will become qd by epsilon naught a. Why? This is my v. Because integral ds 0 to d is just d, which is the spacing between the plates. For the next step, let me write it this way, or I write it this way, use another color, or q is epsilon naught a by d v. Let me name it second. So this is my second. See the plan. First, we assume a charge Q on the plates. Then we calculated electric field between the plates in terms of the charge, which is our equation first. Then we used this equation to relate the potential difference between the plates with the charge. So we got this expression. Q is epsilon naught A by D V. Was the next step comparing equation second with Q is equal to CV, which is the defining equation of capacitance, which implies C is epsilon naught A by D. Let me name it 3. So this is my required expression. So if you have a parallel plate capacitor and we are assuming there is vacuum between the plates, there is no dielectric between the plates, then the expression for its capacitance is epsilon naught A by D. You can see the dependence of the capacitance on geometrical parameters. It is directly proportional to area of the plates and inversely proportional to separation distance between the plates, right? We will continue this topic. First, I will give you some homework. So your homework is question first. A storage capacitor on a random access memory on a random access memory RAM chip has a capacitance of 55 femtofarad. If it is charged to 5.3 volt, how many excess electrons are there on its negative plate. I repeat the question. A storage capacitor on a random access memory RAM chip has a capacitance of 55 femtofarad. If it is charged to 5.3 volt, how many excess electrons are there on its negative plate? It is easy. Remember, 1 femtofarad is 10 raised power minus 15 farad, right? Then question second. Use this color. The question says a parallel plate capacitor, a parallel plate capacitor has circular plates, has circular plates of 8.22 centimeter radius and 1.31 millimeter separation. Then part A, calculate the capacitance. Calculate the capacitance. Calculate the capacitance. Part B, what charge will appear on the plates if a potential difference of 116 volt is applied. I repeat the question. A parallel plate capacitor has circular plates of 8.22 centimeter radius and 1.31 millimeter separation. Part A, calculate the capacitance. Part B, what charge will appear on the plates if a potential difference of 116 volt is applied. So remember, 1 centimeter is 10 raised power minus 2 meter, and 1 millimeter is 10 raised power minus 3 meter, right? This is your homework. Do your homework. Don't waste your time. This is all for today. Thank you. And don't forget to subscribe my channel. God bless you. Assalamu alaikum.